Students, now let's begin with the next very important standard formula. It is going to be y is equal to e raised to ax into sine bx plus c. Now, the way we are going to see the derivation for y is equal to e raised to ax into sine bx plus c, in the exact same manner, we will be deriving the standard formula y is equal to e raised to ax into cos bx plus c. So let's proceed for y is equal to e raised to ax into sine bx plus c. Now students, this is a very important derivation because it is going to bring some concepts back from your 11th and 12th standard. You need to have the concept of compound angles very clear in your mind. So let's begin with the derivation. So as I said, we have to derive the nth order derivative of y is equal to e raised to ax into sine bx plus c. Now try and understand. Here again we are going to make use of the concept of generalizing to find the nth derivative. So I need to find yn here. So students, observe carefully. I'm going to call this as equation number 1 and I'm going to differentiate both sides with respect to x. Let's get y1. Once I get y1 and then later on I will see whether I can generalize the derivative for yn. So to get y1, what I need to do? I need to differentiate this particular function with respect to x. Now, do you observe this is e raised to ax into sine bx plus c. So e raised to ax is a function of x and sine of bx plus c is also a function of x. So this is nothing but the product of two different functions of x. So I certainly need to make use of the product rule, the u into v rule, to find the derivative. So let's make use of the u into v rule. So I get y1 is equal to, this is u into v. So I write e raised to ax as it is, isn't it? The first function, if I say as it is, derivative of the second function. So who is the second function here? It looks like sine x. Derivative of sine x is cos x. But this is not x. This is bx plus c. So I need to again differentiate bx plus c. So I get the derivative of sine bx plus c as cos bx plus c into again the derivative of bx plus c, which is b. And then students, plus take the second function as it is. So I write sine of bx plus c as it is, derivative of e raised to ax. Now I know the derivative of e raised to x is e raised to x. This is e raised to ax. That means again the derivative will be e raised to ax into again the derivative of ax using the composite function or the chain rule, I can say. So the derivative is going to come a. So now if you observe this, the derivative of y1, you can see that e raised to ax is a term which can be taken out common. So let's bring e raised to ax common from the two terms. So what do I get? I'm going to rearrange the terms. I get a into sine bx plus c plus b into cos bx plus c. Isn't it? So that's y1. So I'm going to call this as equation number 2. Now this is where the real challenge starts, students. Now what I'm going to do is I'm going to make this derivative y1 to look like y is equal to e raised to ax into sine bx plus c. That is what my challenge is. I should generalize the terms, all the derivatives should look alike, isn't it? So if y is written as e raised to ax into sine bx plus c, this y1 should also look e raised to ax into term of sine, isn't it? So whatever the angle comes, bx plus c or any other thing comes. So I need to make this y1 to look like y is equal to e raised to ax into sine bx plus c. So here I'm going to carry out a simple procedure. Observe the procedure very carefully. Students, I'm going to transform this entire term into sine bx plus c. I already have e raised to ax, isn't it? So now my worry is to transform this particular term a sine bx plus c plus b cos bx plus c into what? Into sine of bx plus c. Let's see how it can be done. So for that I'm going to take an example. Observe very carefully. Let's take an example. If I give you 3 square plus 4 square. What will you write? So 3 square we know it is 9, 4 square it is 16, isn't it? So 9 plus 16, that comes 25, and 25 I can definitely write it as 5 square. So 3 square plus 4 square is equal to what? It is equal to 5 square. So is it okay if I divide throughout by 5 square? So if I divide throughout by 5 square, I get 3 square upon 5 square, which is 3 upon 5 the whole square plus 4 upon 5 the whole square is equal to 1. Now observe very carefully. These numbers 3 upon 5 and 4 upon 5, these are numbers which are less than 1, isn't it? So 3 by 5 and 4 by 5 are numbers which are less than 1. So can I say this 3 upon 5 can be taken as cos alpha, isn't it? Cos alpha. And for the same angle alpha, if you try to get sin alpha, you will definitely get it as 4 upon 5. The reverse is also true, students. If I take some angle, say beta, say sine of beta is 3 upon 5, then cos of beta will definitely be equal to 4 upon 5. Let's take another example to understand this. I'm going to take a very well-known example, an example that you can relate with. I'll take another example. Observe carefully. If I say root 3 upon 2 the whole square plus 1 upon 2 the whole square, what is the answer? Students, if you can observe here, I've taken root 3 and then 1, and this 2 was actually on the other side, so I brought it down over here. So root 3 upon 2, that gives me 3 by 4, 1 upon 2, that gives me 1 by 4. So 3 by 4 plus 1 by 4, how much does it become? It becomes 4 upon 4, which is 1. That means root 3 by 2 the whole square plus 1 by 2 the whole square is 1. Now observe again very carefully. These numbers are definitely numbers which are less than 1. Now, don't you know that cos of 30 degrees is root 3 upon 2, and at the same time, what is sine of 30? It is 1 upon 2. So can I say this is actually cos square 30 plus sine square 30? It is equal to 1. So the same thing is true for this particular expression also. 3 upon 5, 4 upon 5 can be cos alpha and sin alpha. So that becomes cos square alpha plus sin square alpha is equal to 1. So likewise, in this case again, I know that cos of 30 was root 3 upon 2. What about sine of 60? Sine of 60 is also root 3 upon 2. So I can say sine square 60 plus, at that time, what is cos of 60? So cos of 60, we certainly know it is 1 upon 2. So it comes out to be cos square 60 is also equal to 1. So can you observe the same numbers can be considered for two different angles. One time it was 30 degrees, so cos square theta plus sin square theta. One time it was 60 degrees, so again I'm getting say sin square phi plus cos square phi is equal to 1. So this is a very important example which I'm going to make use over here. Now observe the terms which are accommodated with sin bx plus c and cos bx plus c. What numbers you can see that they are associated with sin and cos. So there is this a and there is this b. So I'm going to take these two numbers a and b. Let us do square of them. Let us add them. So if I say consider a square plus b square. I have taken the two numbers. I have done the square of the two numbers. I have got a square plus b square. Now students, remember that a square plus b square will not give me anything. It is still going to remain a square plus b square. It is not going to become a square b square, isn't it? So it is just an addition of two numbers, a square then plus b square. So nothing is going to happen to this particular term. But observe this thing very carefully. A square plus b square, is it okay to write this as root of a square plus b square the whole square? Observe carefully what I have done over here. I have taken the two numbers a and b. I have done the square of them. I have added them. So a square plus b square. Now I know nothing is going to happen to a square plus b square, but observe carefully what I have done here. I have written a square plus b square as root of a square plus b square, which does not become a plus b. Very important. Root of a square plus b square will stay again as it is. It is not going to become a plus b. For this to become a plus b, this entire expression should have been a plus b the whole square. only then you can write the answer as a plus b. So here at this moment, root of a square plus b square, nothing is going to happen. So it remains as it is. But if I do the square of it, what will happen? The root and the square will cancel. You still get what? A square plus b square, which is nothing but LHS. So observe carefully how this a square plus b square was written. Now, the way I have divided this entire equation throughout by 5. Here also I'm going to divide this entire equation by this particular term along with the square. So I can say divide throughout by root of a square plus b square the whole square. So if I divide throughout by root of a square plus b square the whole square, what will happen? I get a square upon this particular term. So that's a upon root of a square plus b square the whole square, isn't it? Plus b upon root of a square plus b square the whole square. This is going to become equal to what? You are dividing the entire equation throughout by root of a square plus b square the whole square. So here the same term is going to come in the denominator. They both cancel and you get the answer equal to how much? It becomes equal to 1. Now students, there are two different ways in which I can proceed further. I can say a upon root of a square plus b square. I can take this term as sine theta. I can take any value that I want, and when a upon root of a square plus b square is sine theta, at the same time for the same angle theta, this root of this b upon root of a square plus b square, this particular term will definitely become cos theta. So a upon root of a square plus b square and b upon root of a square plus b square, these terms can be taken as sine theta and cos theta, because I know sine square theta plus cos square theta is going to become also 1. So the first term can be taken as sine, the second term can be taken as cos. So observe here, your sine is associated with a, and a you are taking as sine theta, b you are taking as cos theta. Don't worry about the term root of a square plus b square. I'm going to get that term in a short while from now. So a is associated with sine, b is associated with cos. So I get here sine theta, sine bx plus c, cos theta, cos bx plus c. So now, don't you recall, if I give you sine alpha sine beta plus cos alpha cos beta, what does this look like? So if you observe, this is sine alpha sine beta plus cos alpha cos beta. This is the formula, the compound angle formula for what? This is the compound angle formula for cos of alpha minus beta, cos of alpha minus beta. So I have changed a and b into some numbers. The numbers are sine theta and cos theta, and this entire expression has now transformed into a compound angle of cos alpha minus beta. So this has become e raised to ax into cos alpha minus beta. But what do I want? I want e raised to ax into sine bx plus c. Sine alpha plus beta or sine alpha minus beta should come over there, isn't it? So here now this a and b, my choice that a is going to be sine theta and b is going to be cos theta is not the correct choice. I have to reverse the values. That means I'm going to say that a upon this root of a square plus b square, I'm going to take it as, say, cos phi, and let's take this b upon root of a square plus b square as sine phi, isn't it? I've picked a different angle now, but again the values will be true for cos square phi plus sine square phi is equal to 1. So students, now you can understand why this thing has been taught, isn't it? Now this is not the part of the derivation that we are doing. You can simply skip this particular part. So this was only for the purpose of explanation about the numbers a and b that I've taken. So here I'm going to take this a upon root of a square plus b square as cos phi. So I'm going to write here, let a upon root of a square plus b square is taken as cos phi. Now students, if a upon root of a square plus b square is taken as cos phi, what does a become equal to? A becomes equal to root of a square plus b square into cos phi. So a becomes what? Root a square plus b square cos phi. Likewise students, I'm going to take b upon root of a square plus b square as sine phi. So b upon root of a square plus b square, I'm going to take it as sine phi. So from here, what does b become equal to? It is going to be root of a square plus b square into sine phi. Further students, let's divide these two terms. So if I divide them, what is going to happen? I'm going to get b upon a. So therefore I can say b upon a becomes equal to the root of a square plus b square cancels. You get sine phi upon cos phi. You get here sine phi upon cos phi, which is tan phi. So from here I can say phi is going to be tan inverse of b upon a. So now I can go back to y1, isn't it? So let's go back to y1. And students, if I ask you now to write the formula for sine of alpha plus beta, what is the formula going to be? Sine of alpha plus beta, we all know it is sine alpha cos beta plus cos alpha into sine beta, isn't it? That's the compound angle formula for sine of alpha plus beta. So now students, let's go back to this y1. Let us rewrite the term of y1. So I'm going to get y1 now as y1 becomes equal to, I already had e raised to ax, so that first term is going to come there. I write e raised to ax, then let's put a bracket. Then you have this a. You tell me what is the replacement available for a now. Look at this, students. What is a? It is root of a square plus b square cos phi. So a is going to get replaced with root of a square plus b square into cos phi into sine of bx plus c, sine of bx plus c, then plus sine, then plus sine. What is b now, students? What is b? It is root of a square plus b square into sine phi. So b is root of a square plus b square into sine phi. Into what do we have further? We have cos of bx plus c. Now you can very well see that you can definitely take out the root of a square plus b square term common. So let's bring it out. So I have this root of a square plus b square common. Then I have this e raised to ax. And inside the bracket, what is going to happen now? I'm going to rearrange the terms. Let's rearrange the terms. I get sine of bx plus c into cos phi plus cos of bx plus c into sine phi. So this definitely looks like the formula sine alpha cos beta plus cos alpha sine beta. This is the formula of what? This is the formula of sine of alpha plus beta. So I get my y1 as root of a square plus b square into e raised to ax into sine of bx plus c plus phi, isn't it? So I'm going to call this as equation number 3. So I have got y1 now, students. So from here itself, I'm going to now start the generalizing to get yn. Now try to understand this. If you try to get now y2, let's analyze what will happen for y2. So if I try to get y2, will this term be a constant? Root of a square plus b square is a constant term. Nothing happens to it, isn't it? It will simply come outside the derivative. So I write root of a square plus b square as it is. Then inside the bracket, what is going to happen? You will be getting e raised to ax into derivative of sine, which is going to be cos, again derivative of this bx plus c plus phi. You know phi is a constant term from here, isn't it? What is phi? Phi is tan inverse of b upon a. So it's a constant term. So derivative of sine is going to become cos bx plus c plus phi, then plus sine term as it is e raised to ax, derivative is going to be e raised to ax into a. So are you observing all these steps will start repeating, isn't it? All these steps are going to repeat. Here you'll get plus phi, here you'll get plus phi. Getting or not? Sine of bx plus c plus phi, cos of bx plus c plus phi. You get again a, you get b. Again you take the numbers, you divide with root of a square b square. Again you take cos phi, you get sine phi, and so on. The terms will again get replaced over here in place of a and b. Again root of a square plus b square is going to get common. This is going to look like sine of bx plus c into cos phi, cos of bx plus c into sine phi. Again here plus phi is going to be there with bx plus c. So this is again going to change to exact this term, bx plus c plus phi, and another plus phi will also come, and one more root of a square plus b square will come outside. So your answer will look something like this. You get root of a square plus b square raised to, you can say 1. Now it will come raised to 2, isn't it? This is raised to 1. Then you will be having this e raised to ax term, e raised to ax term. Then we'll be having the term of sine. So it is sine bx plus c plus, here you have 1 phi. Now you get 2 phi, and so on. You can keep on proceeding further till the nth derivative. So students, I'm going to generalize this now. So therefore I can say in general what is going to be the nth order derivative. So yn can be written as this root of a square plus b square raised to, I get for y2 2, for y1 I've got 1. So for yn I will be getting root of a square plus b square raised to n, isn't it? Into, again I have this e raised to ax, so I'm going to write this e raised to ax into sine of, I get bx plus c plus n phi. So students, here I'm going to do some replacement. Observe carefully. This root of a square plus b square, I'm going to call it as r. So this becomes r raised to n into e raised to ax into sine of bx plus c plus n phi. So what is r over here? You can say that r is root of a square plus b square. So I will write here where r is root of a square plus b square. And what do you know about phi? So phi is nothing but tan inverse of b upon a. So this is your nth derivative, students. This is your nth derivative of y is equal to e raised to ax into sine bx plus c. Now again I'm telling you, this particular stuff that I've written is not required while writing the solution for this particular function y is equal to e raised to ax into sine bx plus c. You just need to carry out this derivation and this part of the derivation. So students, here we have learned how to find the nth derivative of y is equal to e raised to ax into sine bx plus c, and the answer that we have got is r raised to n e raised to ax sine bx plus c plus n phi. What is r here? It is root of a square plus b square, and what is phi here? It is tan inverse of b upon a. Students, I'm going to make use of this particular formula to then again derive one another standard function where in place of e raised to ax, I'll be getting some number, say k raised to x. So you need to remember this particular formula very properly. So students, that was all about this particular derivation. Now let's proceed ahead with the next standard formula.